This is Group 2's presentation on DACs and ADCs with a focus on ADCs, also known as analog to digital converters. Computers are digital devices, meaning that it speaks in a language known as binary, which are either 0 or 1. In the real world, we don't operate on zeros and ones. So how are we able to communicate from the real world into the digital world? We use ADCs and DACs. An ADC takes information from the real world and transmits it into the binary that technology can read. A DAC takes information, digital information, and transforms it into real-world data that we in the real world can see, as opposed to a ADC. The process is basically backwards in comparison. With an ADC, information is brought in to be transformed into information into the digital world, meaning that the more we put in, for example, samples of information into the circuit containing an ADC, the more output we have for the circuit. Here's an example of how to build an ADC. We have the reference voltage, the analog input, the encoder, and the outputs. In this example, our reference voltage is 12 volts, and our input is 4.9 volts. In this example, we have 8 resistors, meaning that across 8 resistors, 12 volts is divided. And here we have each volt being equal to 1.5 volts. So going from the bottom up, we add 1.5, and it'll add to a total of 12 volts. In an ADC circuit, if the input is larger than the reference voltage, then the comparator output will be 1. Here we have the numbers listed out, with 1.5, 3, and 4.5 being less than 4.9. All 3 of these outputs, because they are on or high, go to the encoder. But which output does the encoder read for its output? Well, 3 is the highest, most significant output from out of these 3 voltages. So it's going to take the 3 and read it as its output. It takes the 3 and puts it into binary, the language in which a device will be able to read and understand. Here is the pin diagram for a ADC chip, also known as an 0804 chip. Here is what we're going to be testing: 1 volt, 2 volts, 3 volts, 5 volts. And a 0804 AD chip has about 255 resistors. So we're going to divide that by 5 volts to give us an average of 19.08 millivolts over each resistor. So here's the math that we're doing, and this is the calculations for what we should be getting as our calculated binary. Here is our built circuit. Here's the chip, And here is the outlet indicators. Here currently I have the power and ground connected to the 10K pot, measuring the voltage across the entire circuit. The more I manipulate the resistance will determine the voltage across the entire circuit. Currently, I have the resistance moved and amplified to give me 1 volt. Currently, there's 1 volt moving across this circuit. So looking at the indicators, we have 0011, 0011, which corresponds to the calculated measurements in binary, and in decimal is equivalent to 51. I move the resistor knob to give me about 5 volts across the circuit. This corresponds to all the lights being high, which is what we calculated to get, which is correlated to 255. This concludes Group 2's presentation on ADCs.